Okay, now we're going to look at methylcyclohexane, which methylcyclohexane is a very simple structure. Now that we know where the hydrogens are with the axial and equatorial and all, so here is methylcyclohexane, and remember how we draw the cyclohexane in a ring, in a chair conformation, is parallel lines like this, that, right? So I want you to start drawing your methyl group here in axial position. Always start from there. You will see later on also that it will become very useful for us. So this is the one chair conformation. The other chair conformation, which is the flip, is going to be like this, and remember, parallel lines like this, and then boom, you can join that. So now technically what happens is that this carbon, when you flip it, it becomes this carbon. Okay, now this is axial, so you know, as we talked about before, all axials will become equatorial, so this is going to become equatorial. Okay, this is axial, this is equatorial. This is axial going up, and this equatorial should also be going up. So this is what I'm going to show you in this video. Okay, so here is our structure. Right here you can see that this is the cyclohexane is standing very nicely on the 3 axial hydrogens. Okay, and then here is the axial hydrogen, and I've put the methyl group here on this top carbon. Okay, just like I showed you here, it's right here on the top. This is the carbon with the methyl group. So now what we're going to do is flip, right? So flipping it takes it up here. That's the boat conformation, which we never study, and then here is the other conformation. So this is the other chair conformation. So now the methyl group is equatorial, and I'm not lying to you, right? Here it's equatorial going up. All right, this is axial going down, this is equatorial going up. Again, flip, and this is axial going up. Okay, so now the thing is, which one is a more stable conformation? So first of all, we proved one thing, okay, and that is the whole thing about flipping of chairs, is that, you know, the location of the group has changed. It has changed from axial to equatorial. Before we were looking at hydrogens, axial, equatorial, it didn't really matter because you couldn't see the difference. Now you can see the difference. Okay, and how is that difference affecting us? The affecting us is because of steric hindrance. So here you can also see from the side, okay, of how close these atoms are to each other. Okay, and remember the word for it? Yeah, steric hindrance. Okay, so when this group, the methyl group, when it is axial, it is kind of like fighting for space here. Okay, now let's look at the methyl group in the other flip side. Okay, and now look at this. Now the methyl group can spread out. It's got all its room. It's one. So what do we have now? This is less steric hindrance. So which means what? It means that the group, the methyl group, is going to prefer this conformation. So which means that the cyclohexane stays in this conformation in the lower energy state. The other conformation is a higher energy state because of steric hindrance. We're not going to be dealing too much with the dihedral angles unless we're talking about, you know, other things, which we will later on in the chapters. Then we will talk about some of the relationships to other groups. But right now the dihedral angle is not as much of an important thing as steric hindrances. Okay, so the steric hindrance is a lot. Now imagine if we had more groups, which we're going to do in a minute or two. But here you can see that this is axial, not very stable, but here is the equatorial, and now it is quite stable because of less steric hindrance. As a rule of thumb, you can always say that the more groups you have in the equatorial position, the bigger groups are going to be in the equatorial position, the more stable the structure is going to be. Okay, because in equatorial position there is more room for these big groups. Okay, so that's something that you should keep in mind when you're doing these kind of conformations.